Let's now try an entirely different kind of example. This will be the third example for our course. And this is different because it's going to get us into a continuous charge distribution. I'll make some things similar to what we're familiar with, but the main thing that's going to be different is the nature of the charge distribution. So once again, I'm going to have my nice x-axis. This will be my x-axis. And I will, once again, be thinking about what the electric field is doing at some point along the z-axis, which I will denote again by an open circle at distance z here from the origin. And the question again is going to regard what is the electric field at that particular location. Now what's going to make this a bit different is how the charges are distributed. Rather than taking some point charges and locating them at specific locations, say along my x-axis, instead of doing that, what I'm going to do is I'm going to distribute the charges evenly across the entire x-axis. You can imagine that somehow I take a piece of wool, and that x-axis is one of those materials that when you rub it with wool, you generate, like a lucite rod or something, you generate static electricity. So I'm going to coat this rod with all kinds of charges, and I'll imagine I use the proper form so that I end up with a positive charge on that axis. It doesn't really matter in terms of the variables we're using in the problem. The key, though, is that this charge then is going to be distributed uniformly across that axis. Now, in real, and it's going to be infinite, too, just to make the mathematics a little bit simpler in the end. Now, of course, in real life, what would happen if I made this thing a positively charged system? What that would mean is I've taken the atoms on the surface of that wire, and I've ionized a good number of them. So there's a series then of small, tiny positive charges along this wire. I could try to sum up the effect from all of those individual charges, but there are going to be, trillions of those. And so the calculation then would become completely unwieldy. And it's also unnecessary because we don't need to know the exact details of where every last atom is located in order to calculate this electric field. So let me sketch out the charge then. I'm going to sketch it out by, kind of hashing in the line here. These little hashes are supposed to represent, what we call a continuous, a completely smoothed out distribution of our charges. Now, to calculate the electric field, one of the first things I would like to do actually before calculating it, I guess, is to use whatever intuition we have. What can we guess about this particular system? Well, one thing, again, that we can always guess at is the direction of the electric field. So once again, I can imagine what would happen if I have this infinite wire and I put a small positive test charge right here at this location along the z-axis. Well, I think we know what would happen, particularly if this wire is positively charged. My positive test charge would be very quickly repelled by that wire. It would want to get away from it as quickly as possible. It would tend to go straight up. If that intuition doesn't immediately come to mind, notice that all the charges over here will be generating forces that are up and to the right, whereas those on the right side will generate forces up and to the left. And there's equal amounts of charge on right and left in perfect balance, so we should expect then that the net effect is that the electric field vector would just be pointing up. So that's our guess, at least, for the direction of the field. Let's now sit down and consider how we're going to calculate this. And I'm going to, again, take you through this maybe at a little bit more of a formal and pedantic level than I would expect after you've done this a few times that you would be using. But I want you to really see this worked out rigorously at least once, and then you can begin to, as you gain practice, shorten out all the details that you're going to write. So let's begin then how we would always begin, as I've been emphasizing. We always begin with our general formula. And once again, we seem to be working in a situation where we are given the coordinates of various things. So I'm going to go with the Cartesian form once again, which says I have to sum then over all charges in the system. Coulomb's constant in my numerator has the difference between the location r, where I'm calculating the field, and location r sub n, which is the location of the charges contributing to the field, divided by the magnitude of the vector I just wrote in the numerator, but to the third power. Now, the next step, of course, comes into an issue of translating this into physics. Now, as I was saying, I don't intend actually to sum over every exact ion in this system. What I'd rather do is to lump them together, because when they're really close together, they in essence have the same effect on the electric field up here. They're all the charges in any given little chunk of my wire. Here, let's take a little chunk of my wire. Maybe that chunk will have a width delta xn, right? All the charges in this wire are all essentially, especially when I take the limit that this goes to 0, they're all essentially at the same distance and angle from the point where I'm calculating the field. So all the little charges in here have, in essence, the same effect. So I'd like to lump them together in these tiny little chunks. Now, what I just said, of course, is not an exact statement, that this little charge here will have, of course, slightly different influence than the charge there. But at the end of the day, I plan to take the limit where I have a much larger number of these chunks, and I'm just going to make the chunks smaller and smaller. But for now, let's just take a certain chunk size, delta xn. As I go and look in this formula, it's nice to know the size of my chunk, but what I really need to know is the amount of charge in my chunk. So let me denote that. I'll call the charge delta Q for n representing the nth chunk. So, I'm going to have a whole series of these chunks that I divide my wire into. And I now need to know how much charge I have in each little length of the wire. And that's something that I really haven't specified yet about this wire. Namely, I have not specified how tightly I'm packing charges along the wire, because that will clearly influence how much charge is in any given chunk. The way we like to measure that is something called a linear charge density. So linear charge density. And the variable we usually use for that is lambda. And what lambda measures for us is charge per unit length. And I'm going to call that charge density lambda. That's how the charges are distributed on this wire. And in fact, as I was saying, let's keep in mind we're going to make this a positively charged wire for our example. Now I see this got here a little messy, so let me just kind of patch that up. Charge per length. And this distance here is going to be z. Very good. So if lambda is in coulombs per meter, charge per length, the way I can get the charge in a little chunk is to calculate charge should equal then charge per length times length. So delta Qn should be lambda times delta x sub n. And this formula not only makes sense from dimensional analysis, it also makes sense from an intuitive point of view. The more densely lambda I pack charges on my wire, the greater charge there would be in any given chunk. And also, certainly, if I increase the width of my chunk, it will pick up more charges. So it should be proportional to both of these. So this gives me the charge, then, that I should use for Qn. So there's going to be a lambda times delta x sub n in my numerator. Now I open up my parentheses, as I usually do. The first vector here represents the location where I am calculating the electric field. So this is the general formula, electric field at R. And that location is a distance z up in the k-hat direction from the origin, just like we had before. This then is z times k-hat. And then I have to subtract off r sub n represents then the location of my chunk in space. So my chunk, I need a vector to give me the location of that chunk relative to the origin. I need this vector. And so I need to know a little bit more about my chunk. In particular, I need to know its x-coordinate. So I'll call the x-coordinate of my chunk x sub n. And when I do that, this vector then simply becomes that distance x sub n times the direction I'm traveling, namely along the x-axis or the I-hat direction. That completes my vector, and then just like before, the denominator follows by simply copying the vector that I just wrote in parentheses, taking its magnitude, and then cubing it. Very good. So now we have an explicit sum. And notice that I had said that at the end of the day, I want to take a special limit here. I want to take a limit where delta x sub n is going to go to 0. As I make those little chunks smaller and smaller. And as I do that, of course, there's going to be more and more terms in my sum because I'll have more and more chunks that I'm dividing the system into. Now this should start to feel very familiar to you, right? I'm taking a sum, I've got these delta xn's. This clearly is the definition of what is known as a Riemann sum. And we all know what happens to a Riemann sum in the limit as we shrink down the size of our chunks. It simply goes directly over to an integral. So let's carry out that process. So the way a Riemann sum, usually the standard form for writing it down, is where the delta x sub n, we usually like to write that here at the very end. I don't feel like copying it over again, but just imagine I had written delta x sub n over here at the end of the row. So then when we make our transition to an integral, the sum becomes an integral, right? An integral sign, which is just an elongated s standing for sum. Then what goes on inside the integral is the integrand, is everything in here that's multiplying the interval delta x sub n. And those then are the Coulomb constant. I've got numerator and denominator. In the numerator, there's lambda. Delta x sub n, we've moved to the end of the row. We'll handle that in a moment. Then I can open my parentheses. I've got zk hat minus. Now here, something interesting is happening. These x sub n's, right, are the variable that I'm summing over. I've divided x sub n into a series of intervals, delta x sub n. So this delta x sub n refers to my integration variable, as does also my x sub n. And when this carries over to an integral, my integration variable is going to be x. So for x sub n, I'm supposed to just write x. So that's x times I hat. And then, of course, my denominator is just a copy of the same vector, zk hat minus xi hat, power cubed. And the last piece I have to deal with is this delta x sub n. And as I was just saying, that x sub n is our integration variable, and the delta x sub n part, that's what becomes the differential dx. So, the main trick in the transition from the Riemann sum is that everything with a sub n, right, turns into your integration variable, either x or in the delta case, that becomes just your dx. We're almost done now. There's just one last thing, and that is that a Riemann sum always gives you a number for its answer. It's a number, not a function. So we need to use the kind of integral that gives us a number and not a function. In particular, that is a definite integral. This means then I need to have proper limits of my integration. Those limits should correspond to the range of my integration variable, which we just decided was x. So when I look at my line and I ask, well, what is the range of x? It goes, I had said it's an infinite line, so it goes all the way on this side out infinitely towards x equals minus infinity, all the way across the line to this end for x goes to plus infinity. So my integral goes from minus infinity then to plus infinity. And that then gives a complete translation, finally, of the initial formula into a mathematical expression that then we can evaluate using our standard calculus rules. Now, the one thing I'd like to say is that although in this case I very carefully carried out the transition to a Riemann sum, look, we're all grown-ups here, right? We're all physicists mostly and engineers mostly, right? We're not mathematicians. So we're just as happy in this course for you, instead of calling the widths of your little chunks delta x sub n's, you can just right away call those dx. That's fine with us. And rather than writing sums all the time, if you're going to end up doing an integral, you can just write the integral sign for the sum right away. and basically go directly from this formula to here without all of this extra talk about the Riemann sum. I just wanted you to see at least once how we are indeed doing things with significant rigor here in the course, where you can rigorously write down a summation which then turns, using the integral theorem of calculus, directly into a proper integral form. Very good. So, now that it's translated into an integral, our job is to carry out the proper mathematical analysis. So let's embark then on that. We're coming into the home stretch now for this grunge, and we're looking forward, I think, to the next lecture, but you need to know how to carry out these types of calculations. All right, so this integral then gives me the electric field at location z. So let me copy that down before I forget what the whole point of all of this is. And now my job is to evaluate this integral. And there's various simplifications we can carry out. The first thing I think we all know, right, is that the integral of a sum of two functions is the same as the sum of the integrals. Or in this case, it's a difference, right? So I can write this out as one integral representing these pieces minus another integral representing the other pieces. So let me embark on that. So let's look at this part of the integral first, and we'll subtract off the other piece in a moment. When I focus on this part of the integral, I'll notice I've got several constants in here, right? I've got Coulomb's constant, I've got lambda, z actually is a constant, and k hat also is a constant. It's very important to keep in mind, in fact, that our unit vectors, one very nice thing about them is that not only can we manipulate them just like normal variables, they're just mathematical objects. The second thing is that I hat and k hat are also constants, right? K hat always points upward, like so, regardless of the value of x, right? As I go along this line, as I vary my integration variable, the z hat direction is always up. The k hat direction is always up. Likewise, the I hat direction is always to the right. So these are also constants as far as our integral is concerned. So I'm going to use that also then, because being constants, I can pull them out of the integration. The last thing I should do is deal with my denominator here. We've already simplified something like this before. We're going to use Pythagoras' theorem, which will give me the square root of the sum of the squares. So the sum of the squares is going to be z squared plus x squared. My job then is to take the square root of that to get the magnitude and then to cube it. So once again, that will give me a 3/2 power. So as I write down my electric field then, my first term will have the following. I'll have Coulomb's constant that I can factor out. Lambda I'm going to factor out. That doesn't depend upon x. Z itself also does not depend upon x. Notice that z just tells me the height above the axis. That doesn't change as I'm moving my way along the axis. So I could also factor out z if I liked. I'm then left with the integral minus infinity to infinity. Now notice I know I haven't done the k hat part yet. I'll write that last because it gives us the vector's direction. What's left over on the insides then is just my denominator and my dx. So sometimes we write these functions by putting dx over, and then it'll be z squared plus x squared to the 3/2 power. And this integral then is something we will have to evaluate, and we then should not forget to multiply by k hat. So let's see, did we handle all of our factors? Yes, I can see I've handled the Coulomb's constant and the lambda and the denominator. I handled all of those. I also handled the z and the k hat. So I can circle that term as handled. I just have this one remaining term to deal with. So let's do that one. Now it's a subtraction because I had an integral of a difference. That gives me the difference of the integrals. In terms of constants that I can pull out of my integral, again, I've got Coulomb's constant and lambda. That's a constant I can pull out. I then have the integral, and that goes from minus infinity to infinity. I have numerator and denominator. In my numerator now, though, I've got x, and x is my integration variable. x most definitely is something that's changing as I'm summing up here along the wire. So that can't come out of the integral. So I still have an x in here. I hat I'm going to write here at the end. I'll factor that out. It's just a constant. And then what's left is dx. And then I have my denominator, which is z squared plus x squared to the 3/2 power. And that gives me that integral. Woof. Well, we're getting there. Now, there's something very interesting about these integrals. One of them should be 0. Remember, from our guess, we were guessing, right, that the electric field pointed straight up. That means we're guessing that there is only a k-hat component and no i-hat component. So let's look at this integral and see if there's any reason we could find that would tell us that this is 0, so we don't have to carry out the integration. Well, one thing that's very useful for determining when integrals are 0 is to consider the symmetry of the integrand. Is it an odd function or an even function? And notice, if I let x go to minus x, that's not going to change the denominator because I've got x squared here, and that minus sign will go away. There'll be no change in the denominator, but the numerator, x, will flip sign. So this means that this is an odd function. It's an odd function. And if it's an odd function integrated over a symmetric interval, the result of that is 0. Perfect. So I have one other function to integrate. This one we won't be so lucky. Notice if x goes to minus x, the denominator doesn't change, and so this is an even function. This is even function. So that one we still have to do. There's still going to be some answer that's not 0. So continuing my calculation, I then have Coulomb's constant lambda z times this particular integral times k hat. So I'll put parentheses for my integral. Now, for doing the integral, for what goes in here, we have a number of options. I don't want this lecture to run too long for you guys, so I'm not going to work it out for you the old school way. But you can see, in terms of the old school way, that very clearly this looks like a very strong case for some kind of trig substitution. And that's, in fact, how you would want to carry out that integral. The more modern way to do this would be, or a little bit less old school, is the engineers used to carry around actually these giant paper books, giant like catalogs. And what were in them were just integral after integral and the answer for those integrals. So in the somewhat old days, what you would do is you would just look this up in an integral table. Nowadays, of course, you could just type it into Wolfram Alpha. You could use your symbolic calculator. Of course, those won't be allowed on exams. On exams, we'll give you any indefinite integrals that you might need, except for the more simple kind of integrals. If it's tricky, on an exam we'll give you the integral, just like you'll see we do often we'll do on the problem set. So if you actually look up that integral, you'll find it has the following result. It goes like 1 over z squared times x divided by the square root of z squared plus x squared. So now, if we carry this out, what we're going to find then is, in our particular case, we have to evaluate this between infinity and minus infinity. And when you substitute in x equals infinity and minus infinity and subtract these, what you find is that what goes on the inside then will simply become 2 divided by z squared. So then we can get to our final result. The electric field then at distance z from the wire has this interesting mathematical dependence. Okay, it depends on Coulomb's constant. That's fine. In the numerator then, I will have lambda. I have a factor of z in the numerator, but I have 2 factors of z in the denominator, so it goes like lambda over z. There's another factor of 2 here for the numerator, so it's 2 lambda, and then it multiplies k hat. What I find interesting about this result is that unlike a point charge, where the electric field strength drops like 1 over distance squared, here notice that because we've smeared our charge out over a line, now the dependence is different. It's proportional to just 1 over the distance. And this is a famous result, and we should put this in our growing database of electric fields that we've already solved. This is a handy one because charged wires come up frequently in various applications. So I'm going to write down that this is for an infinite wire of charge per length lambda. And I will put a box around our result. And this then will end our lecture for the day. And I promise the next lecture won't get us into quite so much grungy algebraic detail. But once again, these are skills that you are going to need, and it's important that you see us work out this result for you at least once. We're going to be showing you in future lectures some much more powerful methods for analyzing things like this infinite wire. Don't worry, where you'll be able to get this result much more simply. But there are cases where those more powerful methods break down and you do actually have to carry out integrals. So it was important for us to teach you how to handle it so you're prepared to handle any case that you might face in your future career.